Okay, so the first speaker for today is Harald from Freiburg, and he is going to talk about vector fields and integrals. So without further ado, let me just mute myself and stop my video, and yeah, the stage is yours.
Okay, thanks a lot for the invitation to talk. And yeah, so I want to I want to talk about ongoing work with together with my student. It's hard to point here apparently. Together with my student Max Klinkert, and yeah, the general topic is vector fields and integrals. Yes, so as a brief introduction, I have to say that I have not worked directly on elliptic integrals. So in the context of the problems that we encountered recently, I tried to find a few pieces that we learned, which might nevertheless be of relevance for this particular topic, so for elliptic integrals. So I collected a few things, and I hope some of them are new and some less new, and I hope that somehow these structures will be of relevance or helpful to someone. Okay, so I will start with a general motivation. So the bigger picture, the thing that we are after are scattering amplitudes, maybe even cross sections, but let's say at intermediate step, scattering amplitudes. And these computations are, of course, very complex typically, given the number of pieces that go into these computations. And one particular piece that we encounter are, of course, the integrals, or associated to them the number of integral topologies. So there are many such pieces, and typically one needs an automated way to deal with these things. Okay, so computing integrals, as we learned in the recent years, or rediscovered in recent years, have a lot to do with algebraic geometry. And recently, we have made a lot of progress with understanding algebraic or using algebraic tools, or extending our algebraic toolkit. However, it has been difficult, I think, or at least for myself, it has been very difficult to activate the geometric understanding of that's involved in these computations. And so I think very useful, so given these issues, in particular the complexity, one would now like to try to find ways to access more geometric information, however, probably to rely on the algebraic tools that we have in order to get there. Okay, so I want to then use one of such tools, and that has not been discussed in literature too much. This tool, this vehicle that should get us to maybe geometric properties are not the advertised vector fields. Okay, so I will try to add another algebraic tool and try to extract some geometric properties from studying these. Okay, so that's the general plan. And in order to, again, link these things to where we want to go to, I want to discuss where we stand with amplitudes, just briefly, or at least to discuss one approach to computing amplitudes and see where these aspects that I will mention fit in. Okay, so recently we have seen that going to or computing complex amplitudes, at least in particular multi-particle amplitudes, is analytically very challenging, and there have been numerical approaches or mixed numerical and analytical approaches to do that. So there is a new, there are lots of tools being developed in the recent years, and you can see a list of some of the authors on the right-hand side. Okay, so let's see what this amplitude computation amounts to. So there's, you see this list in front of you. Unfortunately, I cannot point to items, but there are many steps required in this computation. So the computations typically start with the parameterization of the amplitude integrand in terms of surface terms and cluster integrals. If we have such a parameterization, one continues to discuss, or one uses generalized unitarity and numerical evaluation to determine coefficients in this parameterization. Another important step when doing these things, in particular when switching to numeric, is to set up the computation to be compatible with numerical evaluations. So this is in particular problematic in dimensional regularization. So one needs a numerical formulation of various items that go into this computation. In particular, one needs to know how to deal, for example, with fermions or various other states numerically. So where one can keep the dimension parameter in an analytic form. Okay, a next step is then to recover the analytic dependence on D. So there's a analytic reconstruction step. So one samples over multiple discrete values of D in order to reconstruct the analytic form of D. An important next step is then to replace. So at this stage, one has computed integral coefficients, and one then multiplies in a function basis in its epsilon x function. One cleans up these things, so one extracts the relevant piece, the finite remainder, and if one wants, one can at that stage then try to analytically reconstruct the analytic form of the coefficients. So that's again using multiple numerical samples in order to reconstruct a rational form of coefficients. And finally, one tries to clean up these expressions. And one way to clean up expressions is using Lennart's partial fraction decomposition methods. Okay, so there's lots of steps that we developed or learned how to handle. And there are a few steps, I think, which are particularly come to mind when thinking elliptic integrals. So I think the one step is the very last one. So if you want to go back to the analytic form of coefficients, it's important to use a good basis for the master integrals. If you do that, then the form of the coefficients is simple or simpler. So I think an important question is always what's a basis of integrals? We know this for what a good basis for integrals, how it is defined for non-elliptic integrals. It will probably be important to find a similar understanding for the elliptic integrals. Okay, so we need a good basis if we want to extend these methods for elliptic cases. Okay, so then there are two places here where vector fields are of importance, and the first place is finding the parameterization of the amplitude, so the very first thing. And then it turns out the next step, there's a second place, and that's actually the numerical evaluation. So generalized unitarity and numerical evaluation. So that's a place where vector fields play a particular role. And we will see that the role they play there is they teach us a bit about the integrands, and maybe that's also linked to finding actually particular forms of the integrands or nice forms of the integrands. So that's in this way, vector fields feed back into finding good forms, or maybe also good forms of integrals. Okay. Okay, so the central object that's relevant for these steps are cut surfaces. So what I mean with this is I want to consider Feynman integrals in momentum space. And I want to consider Feynman integrals modulo pinches, And so if you consider them modulo pinches, this is equivalent to saying that we consider insertions, so tensor insertions, as you see in this equation, modulo terms that depend explicitly on propagator variables. So first of all, so two things get introduced here. So first of all, you have the propagators, or the set of propagators. This set of propagators, they form algebraically, they form an ideal. And we can also associate to this set of propagators a surface, meaning that if we set all these propagators to 0, then we get an algebraic variety. So it's this surface, this algebraic variety that I want to call cut surface. So you see at the same time the algebraic and the geometric picture of this variety here. So one thing is discussing things modulo pinches, and the other thing is setting these propagators to 0. The name cut surface is there just because setting propagators to 0, we usually do this when we study generalized unitarity or unitarity cuts. It makes sense. So these surfaces are actually the surfaces that that we usually parameterize when we do unitarity cuts. Okay, so the natural functions to discuss on these surfaces are then given by polynomials modulo propagators, and these are then these simply function rings that one gets by quotienting by propagators, polynomials by propagators. Okay, so there is a particular set of coordinates that's useful when discussing these cut surfaces, and these are the well-known Bykov coordinates, or maybe Katkowski coordinates. Katkowski, I think, introduced them already much earlier, and maybe didn't go as far as Bykov. In any case, what one does in these parameterizations, one replaces the loop momentum by propagator variables plus additional variables that are just required to cover all the dependencies. Here, the propagator variables are called rho, as we've seen already before, and the additional variables, the irreducible scalar products, are called alpha throughout this presentation. Okay, so doing this coordinate transformation, we then arrive at this form of the integral. So the integral is given as a measure in terms of these propagator variables and the ISPs. And then there's this expression where you still see the tensor insertion T. You see the propagators in the denominator, and then you see this Jacobian factor, the B to the power D. So this is the so-called Bykov polynomial, and it's given as a gram determinant of a gram matrix, as written a bit further below. Okay, so this is a convenient way to write the integral, because now rho is really is not a polynomial function, but it's really a variable, so it's very easy to mod out by rho, and discuss actually the on-shell properties. Okay, so one so going to the on-shell properties maybe at the integral level, one can also do by just taking residues now in the variables, and this sets the rho dependence in the insertion and the Bykov polynomial just simply to 0, and we get a simplified integral here. So maybe a word about the interpretation of the objects here. So B is the Jacobian, but we can also imagine it to be associated to the volume of an internal manifold, which is fibered over the space parameterized by the propagator variables and the ISPs. So you can think of just a coordinate space rho alpha, and over each point of this space, imagine a sphere. If you think 2 loops or 1 loop, then you can think there's a sphere sitting on top of this, and the volume of the sphere is essentially given by the value of B. B, being a gram determinant, vanishes at well-known locations. So whenever the loop momenter, so if you look at the equation, defining equation for B, whenever the loop momenter are turned to lie into a plane parameterized by the case, or whenever their dependency degenerates to lie in a subspace, not the maximal space they could point to, then this determinant will vanish. So in particular, this volume factor then, so if you're in dim-reg and you think that of a one loop diagram and one loop integral, then typically loop momentum takes values in d dimensions, but by Lorentz symmetry, you can rotate it down to 5 dimensions. And this gram determinant then vanishes on the location where the loop momentum further degenerates to lie in a 4-dimensional plane. At 2 loops, a similar thing happens. So at 2 loops, typically you can rotate the 2 loop momentum into the 5th and 6th dimension, and then when they degenerate to lie either in 5 dimensions or in 4, then this Bykov polynomial vanishes. And if you think about the space, so what happens in this space, you then have these 0 sets of the Bykov polynomial, And that at the same time is the place where this internal space that is fibered over the space vanishes. So you have basically the Bykov determines for you a boundary when this internal space goes to 0. Okay, so this is just helpful consideration. So in particular, if you want to construct interesting subsurfaces of your space, which have no boundaries. Okay, so let me just discuss this maybe more concretely in one example, and this is just one of the points I wanted to bring. So I think this formulation brings a nice geometric picture, and probably it is helpful when trying to understand geometric properties or topological properties like cycles associated to particular integrals. Okay, so this example here is just the famous double box. You see in the middle, you see a picture of the parameter space in terms of ISP variables. So the propagators are on shell. Then you have this parameter space. In this case, it's 2-dimensional because you have 2 ISPs. And then plotted in red. Yeah, so this space has 2 complex dimensions and 4 real dimensions. And the lines that you see in red are now the vanishing locus of the Bykov polynomials. You see these various lines, which are, if you plot it correctly, these are 2 real dimensional things, so 1 complex dimensional lines. Okay, so then if you want to consider cycles in this space, then what you have to do is you have to find areas. So subsets of this space, and you can put, first of all, open space, things that look open in the ISP plane, but end on the places where the Bykov goes to 0. So these are then places where, so over each point of this space, this internal space, but at this vanishing cycles, vanishing surfaces, this internal space goes to 0 and pinches off the surface. So so whenever you have an open surface that, however, ends on the 0 set of the Bykov, you get a closed surface. So a candidate for a good integration cycle theory. Okay, so there's another picture of the same story, which is much older, and people have probably an easier time to deal with, and that's doing the maximal cut in 4 dimensions. So that's the picture that you see on the very right side. So when you do that, then it was found some time ago that the parameter space that you find out is 6 spheres here, which are connected and have some punctures in them. And I think it's very, so this is a picture that's very helpful to think of also, and it's useful to link the 2 things. So in fact, the middle picture, the red lines that you see in the middle picture are equivalent to these 6 spheres that you see on the right-hand side. So we said that where the Bykov vanishes, you have a dimension drop, and that then, so the dimensionality, dimension drop, and that corresponds then to these 4-dimensional cuts that you see on the very right-hand side. The various intersection points correspond to the points where the spheres touch. So they are some kind of singular points in this vanishing set of the Bykov. Okay, so the correspondence is not totally obvious, but so one has to realize that in the Bykov coordinates, you can of course go back to the physical momenta, and when you do so, one realizes that one has to invert quadratic equations. So the physical momenta are actually a double cover of the Bykov coordinates. So over each point of this plane in the ISP, you have 2 momenta sitting, and this doubling then takes these 4 lines or these 3 lines that you see in the central picture and make out of these 3 things. You get these 6 spheres eventually. Okay, so I think that's one thing that I want to discuss. So just Bykov coordinates and extracting some geometric understanding from them. And I will now go on and towards discussing vector fields using this picture somewhat. Okay, so some of the important properties that we will use later of these cut surfaces are, of course, that that when we try to consider master integrals or understand how many master integrals we have in a given topology, we consider total derivative, or first of all, we consider all the polynomials that live on this space, and then we mod out by the total derivatives, and that gives us the set of master integrals. So that's the typical IVP reduction idea. Okay, so we know this, of course. So then, particular properties of the surfaces of spaces that that there are actually distinguished subsurfaces here. We've met them already. So these surfaces are given whenever minors of the Gram matrix vanish. So there's a subsurface where the Bikov vanishes, so that reduces the dimension. So this is associated to reducing the dimensionality of the loop momentum. But you can also have minors vanishing, which imply then that the dimensionality is reduced even further. Right? So these are distinguished surfaces, and they are very natural, and one should typically see them in the computation. One should see traces of this structure. Okay, another important property of the Bikov surfaces are its singularities. So the singularities are given by the location where the Bikov vanishes and all its derivatives with respect to the ISP variables vanish. Okay, so these singularities are interesting in the context of computing leading singularities. So when we compute a leading singularity of an integral, we typically look for places for these isolated singular locations. And so understanding these singularities of the Bikov are particularly important. So what happens now in many cases is that the solutions to these equations are not actually points, but they are surfaces themselves. And so it is, I will discuss in a moment now how you actually find isolated singular points starting from the Bikov surface, even in the case where the singular surface seems to be multidimensional. And discussing singular points is of course particularly interesting because we know, at least intuitively, that whenever we have singularities, we go away from ellipticity of the integrals. So we associate this typically to cycles vanishing, or maybe maybe consequently also intersection numbers to simplify. So that's why discussing singularities is also important. One must say, however, that apart from this topological information, it is not so clear how this simplification actually, what's the mechanism of these simplifications that one observes whenever singularities are around. So in fact, one sees simplification also in the IVP reduction, and it's not totally obvious why this is the case. Okay, so I hope we will discuss this, however, in a bit. Okay, so the first thing I wanted to mention now is this idea of maximal singularities. So we discussed already before the singular surface. So in many cases, so finding the singular surface is just is written, it's just given by the zero set. So one first of all looks for the zero set of the Bikov, and then its derivatives. So in particular, so formulated geometrically, one looks for the places where the rank of the differential of the defining equation of the surface actually drops. So where the rank is zero in the case that that you see up here. These singularities are typically degenerate. In particular, if you look at the form of the Bikov, then the Bikov is quadratic in these mean variables. So also the derivatives are then linear in the mu variables, and if you have and then setting the mu's to zero, typically solves this with your singular surface. And setting mu to 0, as I mentioned before, corresponds to 0 pushes, so talking two loops, setting the bike to 0 pushes the 6-dimensional loop momentum into 5 dimensions, putting the mu to 0 pushes the loop momentum further down into 4 dimensions. So of course, having 4-dimensional configurations of loop momentum which solve the cut conditions are easy to find typically. So one typically finds degenerate singular surfaces. So one can now, however, continue and or extend, then apply it recursively, and that's also something that's well known in mathematics. So, for example, you can find this procedure in Arnold's and et al. Book. So, what you do is you take the ideal that defines your singular surface, and you consider the differential of this ideal, and again you discuss the rank, the location at this rank drops, and this will define for you another variety. And applying this step recursively, you will eventually hit the place where you find discrete and singular points, or maximal singular loci of maximal codimension. In a vector field discussion in a moment. Okay, so let's switch to vector fields now. So the interesting, or the motivations for discussing, or the obvious motivation for discussing vector fields is now, first of all, IUP relations. So the IUP reduction, if you derive IUP relations, you take a total derivative and what you stick in there. So you see the equation, the first equation there, you have a vector field, and then you take a divergence of this. So that's where a vector field shows up. There's another interesting thing that you can do with vector fields. So you can naturally construct D-log forms using vector fields. And this, if you construct these D-log forms, they compute certain indices for associated to vector fields. So they compute something about the critical point, the vanishing points of the vector field. So yeah, it would be interesting to see if these D-log forms associated to particular vector fields can actually be exploited for understanding integrals in a better way. And finally, vector fields are interesting because they link to topological information of the underlying surface. And so whenever the topology changes, or if you count a zero set of vector fields, then you get information about the topology of the underlying space. And if a cycle vanishing, then the topology changes, and then you also expect vector fields or new vector fields that have a new set of critical points. So so there's through vector fields one should, so if you find new vectors, you get new IUP relations, and then you have a mechanism to remove master integrals, which you should lose because the cycle disappears. So vector fields also give you a link between change in topology and changes in your IUP reduction. Okay, so some important properties of vector fields that we discuss. So we will always discuss polynomial vector fields. And these vector fields you have written up there, so they can be parameterized in terms of all the vectors that you have in your problems, the loop momentum vectors and the external momentum K, loop momentum vectors L. And this particular form implies that whenever the loop momentum, when you move to a place in loop momentum space where the dimensionality of L changes from D to a lower dimension, then also the dimensionality or the direction that the vector field points to will also change. So if you go to a place where the loop momentum points, let's say in 5 dimensions, then the vector field will also point in 5 dimensions. If you go to a place where the loop momentum is 4-dimensional, then the vector field will point into 4 dimensions. So this means that the vector fields themselves, they are actually tangent vectors to the surfaces defined by minors of the ground matrices. And so in particular, and in formulas, you see this below. So a vector field acting on a Bykov gives something that is vanishing at the locus of where the Bykov vanishes. So you have a vector field acting on the Bykov, which gives back the Bykov. Vector field acting on mu variables, which are minors of the ground matrix, should return again expressions in the mu variables. So these are interesting properties. So they are also tangent to these distinguished surfaces, that we discussed earlier, and yeah. Okay, so then there's another way to see these relations show up, and that's when we discuss IUP relations in Bykov coordinates. Okay. All right. So there are now particular vectors. So these are generic vector fields, polynomial vector fields, but they are vector fields associated to a given topology. And these were introduced by Glutakaida and Kosover some time ago. So they are vector fields which are actually tangent to the cut surfaces. So the derivatives acting on a propagator returns again a propagator. So then this this implies that these vectors are actually in the kernel of the differential of the propagators when you go to the surface where the propagators are 0. So these were introduced initially as particular vectors that you can use for generating IP relations that do not double propagators. However, they have, of course, this geometric meaning that they are tangent to the cut surface. And in fact, their geometric meaning is even a bit stronger than that. So they're not only tangent to the cut surface, but they're also tangent to the cut surface and all its pinches. So in particular, the right-hand side depends on so the index of the propagator on the right-hand side and the left-hand side is the same, and which doesn't need to be the case for tangent vectors. But in this way, they so this is a bit of a stronger condition than for tangent vectors only. Okay, so it's interesting to discuss now these vector fields in the Bykov coordinates. So so you see here the change of coordinates to Bykov coordinates. It's again in Bykov coordinates you then have a sum of. So you have, again, this defining equation of these tangent vectors written up there. It can be solved explicitly. And yeah, so it turns out that if you're in this Bykov coordinates, it's very easy to solve this defining equation for tangentiality with respect to propagator variables. However, what is when you start with a vector like this, usually you lose the condition that these vector fields should be tangent also to surfaces of lower dimension, and that's then a second equation that you have to add in, and that's the second equation you find here. It's for us it will be important only to consider these vector fields on shell. So and the last equation that you find is now the equation, the way the tangentiality equation looks for on shell. So you have a derivative acting on a Bykov should return the Bykov as the equation. These kind of equations, they are so-called syzygy equations, and they can be solved by computational algebraic geometry in a quite efficient way. Okay, so there are various types of these vectors. So one can, actually vectors you can write down explicitly, so-called generic vectors, and they can be written down by, so you see these vectors VG and VB, and can just written down by inspection. So just by taking the equation and symmetrizing in the right way, then you find these first two vectors, and you can always find them no matter what the form of the Bykov is. And then if the Bykov surface is singular, you typically find additional, or you can find additional vectors. So non-trivial CCGs. Okay, so there one sees that whenever you have singularity, something new is kicking in. Okay, so the simplest example here is the one loop examples. On the left-hand side, you see a massless triangle. The Bykov is here just given by alpha 1 squared, alpha 2 squared. The generic vectors are just rotation generators. And this VP vector, which we are maybe less familiar with. And then finally, this particular vector is this so-called scaling vector, which really amounts to a conformal transformation. So this is VS, which has the components alpha 1, alpha 2, and 2. And this amounts to a conformal transformation. So the Bykov, the vanishing set of the Bykov is really a cone, and then there's a conformal transformation that leaves this cone invariant. And the three-mass triangle you see on the right-hand side, there the Bykov is changed. So it has actually this constant C sitting there, and you do not have this. So this is a regular surface. You don't get the non-trivial CCG relations, and you only get these rotation generators and the other vector. Okay, so this is just to get a feeling for what things are. So non-trivial CCGs are always something like scaling transformation locally around the singularities of the Bykov surface. Okay, so it's interesting to study actually the components of these vector fields in some more detail now. And so we have now, the components of the CCG solution. Let's say this. So they are the V's. So if you go to the last equation here, there are the V's, and then there's the F. So all these things together, they form a CCG. And here, well, the equation is written here again. So you have these V's multiplying the derivatives of the Bykov, and then you have one term which is F and times B. So this equation we want to solve, or tangent vectors solve this equation. And now we can discuss this on particular surfaces of the particular places of the flat surface. So in particular, we can look at the extremers. So if you look at an extremum of the Bykov, then the Bykov itself is not vanishing. So an extremum that's not a singularity, then the Bykov is non-vanishing, but the derivatives of the Bykov are vanishing. So for this equation to hold, you need that this f of b actually vanishes. Okay, so whenever you have a CCG solution on the extremer, f of b vanishes. Then you have a second place, which is interesting. So these are the singularities. The singularities of the Bykov. The Bykov itself vanishes, and the derivative of the Bykov vanishes. And because the derivative vanishes, the Bykov itself vanishes quadratically. So if you again put this into that equation, then one finds the VI's have to vanish at the singularities, but the FB's typically do not vanish at the singularities. Okay, so one can now take these observations and play with them. And what one finds is that we can now use the components of the vectors to discuss some of the properties of the cut surface. So if you look for the place where, so if you compute all the vectors and you look for the place where the FB's of all these vectors vanish, then the set of solutions corresponds exactly the number of extrema of the Bykov extrema, which are not singularities at the same time. And these numbers actually correspond to the number of master integrals. So if you can, without doing an IUP reduction, you can just compute these vectors, and for the vectors you can read out the number of master integrals rather straightforward. Another thing that you can do with the vectors is if you look at the V components. So if you set the V components to 0 of all your vectors, then what you get is the maximal codimension singularities of the Bykov surface. So instead of doing an analysis with minors, you can just set these things to 0 and find the singularities rather quickly. You can also turn it around. So if you know what the singularities are, you know a lot already about the vectors, and you can also make their construction simpler. Okay, so another thing that you can do now that you notice, we can calculate actual surface terms using these vectors, and then we can also discuss their properties. So here I wrote down the surface terms for these 3 types of vectors. And what one observes is that these surface terms, they vanish on particular surfaces as well. So on the extremer, the first type of surface terms, so this mg, vanishes. On the singularities, the first two vanish. And also the last surface and last type of surface terms vanishes on the singularities, provided the p vanishes. These polynomials p vanish on the singularities. Okay, so we find interesting surfaces where these surface terms vanish. That's actually quite helpful for the IUP reduction. So IUP reduction, just written down quickly here on shell, is the following. So we have a tensor insertion, the T of alpha, and it gets equated with the number of surface terms and the number of master integrals with a priori free coefficients. And the IUP reduction amounts to computing these coefficients. And one way to solve these equations, so these linear equations for the coefficient, is to evaluate this equation on multiple points. So for the ISP variables alpha, and yeah, so you can do this numerically. And of course, what determines the how easy it is to solve this equation is the number of surface terms, or the number of surface terms, also the number of values of alpha that you have to insert. So what you can do now is you can actually remember that the surface terms vanish at particular places, and you can actually sample these kind of locations. And by this, you reduce the linear system, and you can simplify these computations. You can even go one step further. You can try to understand these distinguished locations even better, and try to line up actually your master integrals with respect to these distinguished surfaces. And yeah, so I believe that will actually lead to understanding better what are good and less good forms for the expressions for master integrals. Okay, so I collected a little bit of information here on how to do that. So you can actually use this information about the singularities to write your expressions in a particular basis. So actually express your tensor insertions in terms of the polynomials that vanish on the singularities, for example, or on the extremer. And you can build up some sort of Taylor expansions of that sort. And I think you can use these expansions to solve the IUP systems more efficiently. But maybe one can even see structures to find explicit solutions to these systems in that way. So I noted here to diagonalize the IUP system. Okay, I was very short here because I think I'm out of time already. So I'm trying to conclude. So discussed vector fields, which are a natural structure associated to Feynman integrals. So there's the cut surface, and then these are properties of the cut surface, so they naturally appear. We have seen that properties of the vector fields actually have an imprint on the IPP reduction. We can find interesting, probably we can use these vector fields also to learn quite a bit about the integrals themselves. So there are these maximal codimension singularities, and I find them very intriguing for discussing leading singularities. And we've seen also this one example where you can use the zeros of the vector fields to count master integrals. So I think it will be interesting to see if there are further things that we can actually learn from the vector fields about the topology. And yeah, finally, of course, for amplitude computations, we need vector fields. So learning about them and finding better ways to get these vector fields will actually also help on that side. Okay, so that's all. Thanks for now.
Thanks, Harald, for such a nice talk. Let's take 2 seconds to unmute ourselves and give Harald a round of applause. So if anyone has any questions, Yeah, okay, I see already a question from Roman Lee. Please go ahead, Roman.
Hi, Harald.
Right.
I want to ask you, you said that there is a, some similar features of your approach with the one that we used with Andrei Pomeransky in our paper to count master integrals. I just want to understand, is it interpretation which is different, or technically it is you do something different to count the master integrals? Because we also used, both Feynman parameterization and Bykov parameterization, and it seems that for Bykov parameterization, you can probably do the only thing that we did.
Yeah, well, I would think it's the same. So nothing new, apart maybe from the fact that it didn't dig into the singularities that much. I think you found the singularities and then maybe you decomposed your solutions, but you didn't. I think you could have gone one step further in discussing degenerate singular surfaces also, in the Bykov representation. But
yeah, connected to this, I would also want to ask a question about, singularities at infinity or critical points at infinity, because you know that, for example, MINT, it gives sometimes less master integrals than there are in this sector. And we do believe, and actually we checked in several examples, that it is connected to the phenomenon of critical points at infinity, which means which comes because we we have to compactify somehow our space, so we don't know how to do it in a proper way.
Yeah.
In particular, how to use commutative algebra to.
Yeah. Well, I must say I'm too experimental, too phenomenological in the moment, so I cannot say anything about this. It would be interesting to have an example actually where this problem appears in the Bykov representation.
Yeah,
and to try it.
It seems to appear simultaneously. So
it's
if it appears
okay.
in Feynman representation, it appears also in Bykov representation. Unfortunately, you cannot get the right answer in both of them. So I can give you.
Yeah, if you have something, would be great. Yeah.
Yeah. Okay.
Okay. Yeah. Thanks.
If anyone else has question, please raise your hands. I have a very general question actually about this good functional basis. So what do you think is the, like, you didn't talk much about what can be considered good functional basis for elliptic integrals. In particular, for example, this pure functions for elliptic multiple pole logarithm, can they be considered a good functional basis for amplitude computation, for instance? Do you have anything to talk about it? Do you have any comments?
Well, I don't have any experience with that.
Okay.
I mean, I don't know of an explicit, at least we have not done an explicit computation where this kind of simplification showed up.
Okay.
Just because we didn't do it. I think the right people to ask is probably the ones that consider the IUP reduction with including elliptic integrals. So I think there should be a lot of experience here. For example, looking at
we can also discuss tomorrow during discussions about this. I see another question from Matthias Falk. Matthias, please go ahead.
Yes, thanks. So I have a question about what you mean by this left elliptic that you said. So does it mean that you start with some, I don't know, high dimensional space and you see it degenerate somehow, or is it more meant in the sense that when you reduce to master integrals, you get less that have some elliptic structure, or what do you mean by this?
Yeah. For me, you're asking me, right?
No, well,
okay.
I don't know. Well, if you have the answer, yeah. Sure.
No, I thought you were asking about my question. Sorry, sorry, that was for Harald.
No, it doesn't matter who answers the question.
No.
So what you refer to the point where it said where it says the more singular the less elliptic, or is that?
Yeah, exactly. Yeah.
Well, I think about the torus, for example. If you have a torus, you have two cycles and they intersect, and this intersection is sort of the critical issue that can lead to elliptic integrals. However, if you pinch the torus so that it decomposes into two spheres that they touch each other at points, then you lose the ellipticity. Particularly, you lose cycle and you lose also intersection numbers. In this sense, if you have singularities, something breaks, and it breaks in a good way, I think.
Okay, but so it's really meant like literally for an elliptic case, and you see the elliptic curve disappear in some sense, or
just elliptic. I think you can, in many cases, you can probably kill intersection numbers if you make certain cycles shrink, right? Or
okay,
vanish. Yeah. And that typically leads to singularities.
Okay, thanks.
Okay, so since we are already out of time, I want to let's thank Harald again